So we covered software engineering. Now I want to go down the stack and talk about just the hardware needs or the compute needs. I think there's two distinct parts to developing a model, and I roughly call them development and then training evaluation. So what I mean by development is you're actually writing the network code, you're writing the model code, the loss function. You're trying to get it to train on some sample of the data, debugging it along the way, looking at the results. It's very iterative. And what you really want in this stage is just like be able to quickly run little training loops and then hopefully be able to use a GUI of some sort to look at results. And I think the solution could be your own desktop or a machine that is dedicated to you that has at least one GPU and maybe up to 4, or a cloud instance that is kind of reserved for you that you can log in and have your environment all set up. So the choice there is desktop or cloud. And then when you have something working, so you can run it on one GPU, but now you're ready to do a search, and that could be for hyperparameters, or maybe there's 3 architectures that you got to work, but it takes a few days to actually train each one. So you just want to launch them all and then see which one wins. Or maybe the model that you're training on is so large that actually doesn't fit on even 4 GPUs. Hopefully not, but maybe you just want it to train faster. So what I want there is I want to be able to very easily launch experiments, review all the results that are getting generated. And the solution could still be a desktop. It depends on the size of your problem. Over-engineering is something we should try to avoid. So if all you're training on is a few gigabytes of data, your model's not too big, and you have 4 GPUs on your desktop, that might be all you need, right? But if you need more than that, then you have a choice between a private cluster of machines that you buy or build, or a cloud configuration of multiple GPU-enabled machines. So the reason it pays to think hard about your compute is because, to some degree, you can say that most advancements in deep learning over the last 5 years have occurred because of additional compute power. So there's a blog post by OpenAI called AI and Compute, which plots seminal results from recent years versus the amount of compute that they used in petaflops. And this is on a log scale. So AlphaGo 0 is like an order of magnitude more compute than Alpha 0, but here they show up pretty close together. I want to say that, yeah, compute matters. So it's like you have more compute, you should be able to train better models. That is true. But creativity also matters. And so there's an appendix to that post, which recent novel results that used only modest amounts of compute. And there's very seminal papers here too, like attention is all you need. So that was used for sequence models, which traditionally used LSTMs and models like that, which are very computationally expensive. But attention is all you need are just matrix multiplies, the transformer architecture, which is actually less computationally expensive, but you can train much faster with that architecture. And Fast AI, I think, is also a good role model for this. They try to do stuff that works really well and is still cheap and easy. So I think it's a good mindset to have. I think it's dangerous to just say, I don't need to be creative. I just need 50 more machines or 50 more GPUs. Yeah, maybe, but if you are creative, you'll get away with less GPUs. So between, when we have to decide between on-prem and cloud, we have to consider a few things. The first is just the basics of how GPUs work, the options that we have in the cloud, the options that we have on-premise, and then we can kind of synthesize our recommendations there. So about GPUs, so Nvidia has really been the only game in town. And Google TPUs are real, and they are the fastest current option. They're only available on Google Compute platform. Intel has been trying to get into the game. AMD has been trying to get into the game. It doesn't make sense right now, but maybe it could make sense in the future. And if we look at the GPUs, there's a lot to take in. So these are the Nvidia GPUs that you could conceivably use for your project. And what I want to do is just kind of go through the different dimensions of how you can make that decision. So first of all, there's a new Nvidia architecture roughly every year. And they always name it after an inventor in alphabetical order. So Kepler, Maxwell, Pascal, Volta, Turing. And then they come out with a server version of the card first, and then a version for enthusiasts, which is like a more expensive card, and then finally a version for consumers. So that would be like the 1080 Ti, the 2080 Ti. And technically for business, you're only supposed to use server cards. The RAM dimension, so RAM should fit meaningful batches of your model. And this is really most important for recurrent models. And then there's the 32-bit versus tensor T-flops. So this is like teraflops in 32-bit computation mode, or teraflops in this tensor core computation mode. So tensor cores are specifically for deep learning operations. So they combine, I believe, a multiply of 16-bit numbers and an aggregate in 32-bit precision. So it's mixed precision is another term you might hear. The reason you would care is because you basically get additional speed for free because you can fit more numbers per kind of unit memory and do less calculation to actually get the result. And tensor core performance is really good for convolutional transformer models. They really benefit from that, more so than from higher memory. And then straight 16-bit computation is enabled by this P100 card, but no other card. The other cards all have mixed precision, which is better than straight 16-bit precision. But if you only have access to P100, doing stuff in 16-bit might be better than doing stuff in 32-bit. The reason for that is because you get roughly twice the flops and 1.5 times the memory per, So looking at the oldest architectures, you have the K80, which is actually what you guys have in lab. And the Titan X. And these guys are like 2 to 4 times slower than the current architectures, so we should really not use them. And so if you are building or buying your own machines, you should not buy these cards. But in the cloud, you might end up using them anyway because they are the cheapest options. And the reason they're cheap is because you buy these things at scale and then you're stuck with them for years. And that's what we use in lab, for example. So Pascal Volta is one generation ago, P100 and the 1080 Ti. So 1080 Ti is actually still pretty good if you're scrounging and you're buying used. And it works really well for recurrent networks still. So it doesn't have that mixed precision computation mode, but it has a lot of memory. It has 12 gigs still. And then in the cloud, Google and Microsoft make P100 available. Amazon does not. But if you use those, then that's a mid-range option. And then Turing and Volta are the current architectures. So this is probably what we should be buying right now, mostly due to the 16-bit mixed precision support. And obviously, the clock is faster. Everything is a little better. The hardware, 2080 Ti, is like 1.3 times as fast as 1080 Ti. But if you switch it into 16-bit mode, it's actually twice as fast. So that's nice. And then Titan RTX and Titan V are both 20% faster than that. And then in the cloud, the V100 is the fastest you can do right now. So looking at how they stack up, the TPU is the fastest. That's only on Google Cloud again. V100 is pretty good. And then 2080 Ti is actually also pretty good. So in the cloud, you got Amazon Web Services, Google Cloud, Microsoft Azure. Those are the heavyweights. And they're all largely similar in function and price. AWS, I'd say, is most expensive. Google has a cool feature where you can connect GPUs to any instance. So you can have an instance with like incredible amount of memory and then connect GPUs to it. Whereas on Amazon, you're limited to their like pre-configured instances. And it also has TPUs on Google. And then Azure has never been recommended by anyone I've ever met. So I don't want to, yeah. And then there's startups that, there's Paperspace, which makes GPUs like more easily and cheaply available. and Lambda Labs, which also builds machines. We'll talk about that. But they also have a 1080 Ti cloud, which could be nice. So I don't want to go through the details of this, but I want to highlight that there's on-demand instances where you definitely get an instance. But then there's also spot instances where you get an instance, but it might get shut down at any time. And those are a lot cheaper. So it's like a 50 to 80% discount. But it's a big downside. Your instance can get terminated. So if you have architecture in place that lets you run hyperparameter search, for example, that can handle failures, then the cloud can be really good because it's actually pretty cheap to use those spot instances. But if you're trying to do just kind of reliable computing, that gets tricky. Google Cloud is about the same. It's a little cheaper. Microsoft is about the same. They also have the P100. On-prem, you got choices between building your own, which is actually pretty easy, and it's a quiet machine. If it's 4 GPUs or less, you can buy pre-built. Lambda Labs, Nvidia, and then kind of server makers make GPU machines. So building your own is about $7,000 for 4 2080 Ti's. I think every single time we've taught this class, at least one person has gone out and built a machine as a result of it. So I think it's fun to do. If you're just starting out, it's a good kind of rite of passage. It takes about a day to build and set it all up. Going beyond 4 GPUs, you're now in server enclosure mode and rack mount, and it's very loud and difficult to do now. So Tim Detmers is a PhD student at UW. He's the GPU guru, so his blog posts are great resources about this. But you should probably buy pre-built because unless you're a solo practitioner, a company's not going to want its employees building machines. So Nvidia is kind of the Cadillac of GPU machines. It's very expensive. Since it's their policy that you only are supposed to use server cards for deep learning, they will only sell you server cards in their machines, which are just very expensive. The V100. Lambda Labs is a startup that basically makes good machines that they use server cards, but they also use consumer cards. And so, for example, these kind of 4 GPU desktop machines, there's a markup. It's about 20%, I think, versus building your own, which is probably worth it. And they load it with all the libraries and make sure it's a good experience for you. They also make server machines. So yeah, the V100. If you see the the Quadro RTX 6000, that's basically a Titan RTX, but just with better cooling. So it's the exact same stats. So the cost analysis that I like to do is basically comparing on-prem and an equivalent cloud machine. And we can also then think about spot instances specifically. So let's say I just want a quad GPU PC just to do my basic development. Should I buy a PC or should I go into the cloud? So I don't want to use K80s. I want to use the modern, mixed precision stuff, high clock speeds. So I'm either going to buy 2080 Ti's or pay for a V100. Those are my choices. Let's say it costs me $10,000 to build or $12 per hour, which is the real price to rent it. And if we look at the number of hours it takes to pay the cloud provider as much as we would have spent to just own it forever, the number of hours is 833, which is, if you run 24/7, is 5 weeks, right? So you could say, well, it'll pay for itself in a month, so we should definitely build our own. But I don't think you'll run 24/7, right? That's very high. But maybe you just, every time, all the hours you spend with work, you're running at least one model. So I call that the 16/5 workload. So it's 16 hours a day, 5 days a week. 16 hours, you're not at work 16 hours, but you launch something, it finishes in a few hours. So at that point, it's 10 weeks. So I don't think it's worth being in the cloud for this quad GPU PC. I think in 5 to 10 weeks, you'll pay for the hardware, just the cloud costs. But with hardware, you have it forever. So it makes a lot more sense. Here's a Reddit post that I saw, which really, this person built basically I think 2080 Ti 3X GPU. And he said, you save $1,200, which is the cost of one of those GPUs, every single time you train on ImageNet if you use your own build instead of Google Cloud Engine, which I thought put it in perspective, And it's also twice as fast because he wasn't using the V100, he was using the K80. But another way to think about it is, well, what if I just want to be able to experiment as quickly as possible, right? So there, it might make sense to go into the cloud because I can spin up a bunch of cloud spot instances, and they will basically, let's say my experiment takes 6 hours. If I only have the quad GPU PC, I need to run 96 hours of experiments. I only have 4 GPUs, so it's going to take me 24 hours to crunch through all of my experiments. But in the cloud, I could crunch through all of my experiments in 6 hours. I just launch 16 spot instances. And that's real, right? You save a lot of time, which improves your iteration cycle, and that's worth something. But the thing to think about that is, what is the price of that? So what number of experiments like this would you have to run before that basically equal the cost of building the machine? It's like 100 experiments. So like after you run 100 experiments, you would have been better off having the machine. So it really kind of depends on how you think about iteration cycle speed and time. So in practice, even though cloud is expensive, it's pretty hard to make on-prem scale past a certain point. So if you have a dozen people working on machine learning problems, you have to keep buying machines. You have to like cluster them yourself. It's a whole headache that cloud solves pretty efficiently. And so that's what I call DevOps, right? So you want to be able to like declare your infrastructure, push updates to all your machines, have some repeatable process and training. That's definitely easier to set up on the cloud than on your own cluster. I think the recommendations differ between a solo practitioner or a small startup versus a large company or a larger company. So for solo, I think you should build or buy a 4x recent architecture PC. And for like scaling up training, I think probably just use the same PC until you know you really have a problem. But if you really do have that problem where you need to run a lot of experiments, you can either buy another machine that's maybe an 8x GPU machine now, or you can then start using cloud instances just for those kind of hyperparameter tuning runs. For a larger company, I think it makes sense to still have that like basic PC per ML scientist, or let them use an expensive but fast cloud instance, which a lot of companies, they're very expensive, so companies are reluctant to do that. And for training and evaluation, definitely use cloud instances because you can properly provision things. You can probably have infrastructure to handle failures. And at this point, I'll pause for questions.
Okay. So to summarize a couple of questions, there's a couple of questions around like what types of data does it make sense to use GPUs for? So for example, we know that GPUs work really well for images. Are they also faster than CPUs with, when you're doing stuff with LSTMs or GRUs on text data? And then do they also accelerate heavy computation on tabular data?
On tabular data?
Yeah.
Yeah, it's a good question. So when does it make sense to use GPUs? I think it makes sense for more and more problems now, because more and more problems have libraries that are able to leverage GPUs. So like the only way it wouldn't be worth it to use GPUs is if there's no way to kind of harness the GPU computational power, like the CUDA libraries, for the problem that you have. But the number of the problems where you can't do that is decreasing. So I think even on tabular data, if you, like that's your input layer, is just tabular data. But then after that, even if you have a fully connected network, and that's kind of how you do predictions, that'll still be a lot faster on GPU than on CPU. And companies like Facebook and Google are open sourcing libraries for all sorts of machine learning problems that leverage GPUs now. So there's a thing called Rapids AI, which does basically pandas on GPU now. So I think GPUs are always going to be worth it.
Yeah, and I think specifically on LSTMs and GRUs, even though it's sort of a sequential process, you might think that you might not be able to take advantage of parallelization. Usually the way that those models are trained is by sort of unrolling all the steps of the LSTM. And so you actually can take advantage of quite a lot of parallelism when training models like that. The next question is, what about cloud FPGAs for inference?
Well, so the tensor processing unit, the TPU, I guess would fall under that. I don't know who asked that, but yeah, so basically specialized deep learning chips in the cloud. I basically only know if TPU is a viable option. I think if you know that something is a viable option for you, then it might make sense. But for the general practitioner, probably doesn't make sense.
How does the changing architecture of GPUs, so more and more GPUs are coming out all the time, does that increase the risk that your machine will be out of date for later libraries?
Does what increase the risk?
So I think the question, maybe whoever asked this question can clarify if I don't get it right, but I think what they're asking is, every couple of years, Nvidia comes out with a new chip that's much faster, right? And so how should you think about that in the decision about whether it makes sense to build versus go onto the cloud?
Yeah, that's a good question. So it might seem like sticking with cloud gets you access to the fastest GPUs faster, but I don't think that's actually true. For example, when V100 came out, it took Amazon several months to roll it out, roll out that instance type. And even after they rolled it out, to get the service quota for actually launching those instances was still difficult. So these GPUs don't magically appear at the cloud providers either, right? You have to buy them, but they also have to buy them. And so there's a process for them to buy and make those GPUs available to you, which is, I think, going to be roughly the same timeline as you buying them. But on the question of depreciation, are you going to be stuck with what you bought even though there's faster options available? I think it's probably still worth it to have your own GPUs because the newer architectures are going to be much more expensive on the cloud. So K80s are still around in the cloud, and they're the cheapest option, and so we're tempted to use them, right? But those are 4 years old now. So we'd never buy them for our own PC, but we end up using them on the cloud and kind of paying the cost in slower experiments.
There's a question about serverless notebooks, so like Colab. And the question is, are there open source alternatives or things that are available to be installed on-prem?
Well, Jupyter Notebook would be an open source alternative to Colab, right? Jupyter is open source. It's a notebook. So you can install it on-prem. I guess I don't fully understand. Oh, easily provision resources on-prem for a notebook? Yeah, I think I'll get to some of that stuff a little bit later.
It was my question. Rather, something that's more on the side of Lambda that's elastically scalable based on the size of the data and compute.
Yeah.
Have a Jupyter style open source software.
Yeah, it was an elaboration on the question, but I still think I'll get to it later in this presentation.